Did you know that the acceleration due to gravity actually decreases the further you go up? Meaning that someone at the top of this tree, for example, would be accelerated due to gravity less than someone that was at the bottom? This actually plays into our problem. Question number 10. Imagine we're on a mountain observatory and we have a sensitive gravimeter. This gravimeter measures the freefall acceleration to be 0.0075 meters per second squared less than normal, or 9.7925 meters per second squared exactly. With this knowledge, how high is it? When going about solving a physics problem, I like looking at the question to see what they give us and what we're trying to solve. In this question, they don't really give us much. They give us only the acceleration due to gravity at the observatory, and they're asking for the height. So I looked into the textbook to see if I can find an equation that had both acceleration due to gravity or just plain old acceleration and height. Luckily enough, I found one. On page 342 of the textbook, we can find equation 13.8. Equation 13.8 allows us to calculate the acceleration due to gravity of any object given Newton's gravitational constant, the mass of the planet, and the distance between the object and the center of that planet. To get equation 13.9, we must first expand the denominator. The radius in the denominator of equation 13.8 can be expanded to the radius of the planet, in this case Earth, plus the height of the object from the surface of the planet. We can then factor out the radius of the Earth, leaving us with 1 plus h over r Earth squared. From this, we can cancel out our r Earth squared on the outside of the parentheses with the gravitational constant and the mass of the Earth, leaving us only with the gravitational acceleration at the surface of the Earth. This is equation 13.9, which allows us to calculate the gravitational acceleration of any object given the acceleration due to gravity at the surface of the planet, and the height of the object, and the radius of the planet. Given the numbers we have from the problem, all we have to do now is isolate h. First, we square root both sides to get rid of that square root at the bottom of the denominator, leaving us with this. We can then rearrange the equation, leaving h on one side by itself. Subtracting 1 and multiplying by the radius of the Earth leaves us with this equation. From here, all we have to do is plug in our numbers. Here we have a final answer of 2,438 meters, or 2.44 kilometers. That's 5.5 Empire State Buildings tall, which is quite high. Well, this number actually makes quite a bit of sense. Think about how high the International Space Station is. It's in space. Yet, it's still affected by Earth's acceleration due to gravity, being accelerated at 8.8 meters per second squared, only one less than Earth's normal gravity at its surface. Meaning that a small change to Earth's acceleration due to gravity can have a wild change in the height of an object when we're calculating it. So to recap, we can calculate the height of any object given a few parameters, meaning that we can actually substitute any of these numbers for a different planet such as Jupiter. That could be pretty interesting to try out. So if you guys need more practice, I suggest trying it out with different accelerations and different planets possibly. Anyway, that's all from me for now. See you later, and thanks for watching.